Hello, everyone. Thank you so much for joining. I'm Pawan Khandavilli. I'm a senior product manager on the Azure Confidential Computing team at Microsoft. And today I'm here to talk about how confidential computing technology that this community has been building and taking forward solves a new and urgent problem in the AI space. Just before I begin, this is not a Microsoft product. Views expressed here are on my own, and not do not represent Microsoft's official position. So I just want to make sure we get the disclaimer out of the way. And so the talk today will have three main portions, right? Like we have the problem on why MCP servers are uniquely high value targets and why some of the existing controls might not work. Uh, the solution on how do we close the gap with using confidential computing as a defense in depth, and the framework on how to think beyond trusted execution environments and confidential computing to protect the full threat surface of your MCP servers. So that's where the talk will go today. So let's get started. So for those, this is a bit of an orientation slide for folks who are not following this space. So confidential MCP servers, short for Model Context Protocol Server, uh, are sort of the USB-C of agent tooling, right? Like it's like a universal interface for LLMs and agent harnesses to sort of talk to the external world uh, and do real world actions. Like this is one of the reasons why adoption is exploding. Almost every major AI framework is adding MCP support, and that gets it to the second row, where to talk to this external world and have all these accesses, so you need credentials, right? Like it could be GitHub, AWS, Slack, Stripe, whatever it is that you need to access and do things outside in the real world. You need that access. So we have a credential aggregation problem here, and just going beyond that, like LLMs, the LLM intent is transferred into the real world through MCP server execution, as I mentioned before, and lots of credentials and sometimes your entire stack uh, can be part of this, which can be a single point of compromise. So the right way to think about MCP is not as a tool layer, but a capability system. That means you need permissioning, isolation, auditing, and blast radius control. And I'll be talking about isolation and blast radius control through this talk, and we can, at the end, touch upon some of the other things we can do. So this slide, I'm trying to bring together what we mean by the credential aggregation problem, right? This is a realistic example of how a remote MCP server would look like. That's maybe engineering focused or developer focused, right? So it could have GitHub tokens, Slack tokens, etc., that are loaded that the MCP server uses to communicate. And before we go further, like I know MCP is a lot. It's a open protocol. There's ways to extend it. So there's local MCP servers, local MCPs and MCP servers that are hosted remotely. I'm not going to talk about the local side today because they run as child processes and they have a different threat model. What we're focused on is remote MCP servers deployed as a service, shared across users or agents, running on cloud or hosted infrastructure. And that's where this threat model sort of applies. So if you think about this, all this credential aggregation, the blast radius is pretty high, right? Like if you, this could be depending on the access control and other permissions that are part of these tokens. It could be read write to all GitHub, perhaps, and even sometimes full database access. So the blast radius of a memory dump or being able to get these credentials is pretty high. So uh, so just to sum it up, to make your LLMs and agents useful, they need to use MCP to talk to the real world. And the more the tools you add to make it work for you, the larger the blast radius. So there are controls that are in place, right? There is IAM, role-based access control, and other controls. So we can go each one one by one, and we have uh, IAM and RBAC, which assumes the host is trusted again, but this does not prevent any memory reads, secrets vault. This is very good in practice. It needs to be there, and this protects data at rest and the secrets at rest. But once they get into the MCP server so that they can be used, that's when they get vulnerable. And just by the way they work, MCP servers do have to talk to the external world to be useful. So there is external outbound network policies that let the MCP servers talk to this external world. So there could be exfiltration. And then container isolation. This is another good practice where you build containers to run these servers. But again, if you get access to the host, all these controls sort of go away. And we need to remove the assumption just because of the credential aggregation and blast radius that we have with MCP servers. So again, the core problem is you could, if you gain root sort of host access, you can inspect the memory, extract the secrets, and then we will be able to exfiltrate via HTTPS. So let's talk about how confidential computing can help prevent these attacks, right? I'm sure folks who are familiar with confidential computing kind of see where this is going. So for each T property, there is a thread that's closed. So the first one, which is memory encryption, you can dump the memory to try and get the credentials, but all you see is ciphertext, and you can't gain access. Remote attestation. Think about tampered image. If you apply remote attestation and verification the right way, even though if it gets deployed normally, key vault checks and other checks where you could gate the credentials will not be able to pass because the attestation will show that this is an image that hasn't been approved. Attestation gated credential delivery, like this is what we call a secure key release in most scenarios. So any secret that needs to be loaded to the MCP server, whether it be baseline credentials that you need to talk to a surface versus scope tokens that agents might send per session. All of this can be gated based on the attestation. Code integrity, like it can help with supply chain attacks, like if there is a malicious dependency that gets into the container build, the CPU can measure the entire image at launch. So if the measurements don't match the known good hash, then the key release attestation, all of them will fail. So this can catch supply chain attacks that could lead to exfiltration. And the final one, which at least is my favorite when it comes to TEs and confidential computing, the the measurement becomes sort of the cryptographic identity, right? Because the same source code and the build process always produce the same measurements. I know this could be tricky to get right, but this does get to the same measurements. And then once you publish the known good measurement, any relying party, including the agent orchestrator, control plane auditor, like can verify via remote attestation before connecting. And this is the identity at the hardware level. And that cannot be forced easily. So all this gives sort of the right properties to close the threat models that we're seeing. And I just want to add a bit here, because when we talk about protecting AI workloads, we think about GPUs a lot, and they are very important. We need to have the right GPU support. I'm glad that we are investing in confidential GPUs, but all of this MCPs are not GPU-bound workloads. These are like CPU workloads that can be protected with the current CPU technology that we have. I know we're getting GPUs, but this is something that we can do beyond the work that is already being done on the GPU and the ecosystem around it. So one pattern, right? This is the same architecture that can be reused to protect MCP servers. So we need a hardware TE. This could be AMD SCV Intel TDX, or ARM CCA. All this encrypts VM memory in the silicon. Confidential containers, like this fits right in because it provides the ability to provide these measurements and use them. We need an attestation service to verify and validate the hardware codes that the relying party can use, and also gated key release policies that secrets are bound to the attested code measurements. So these patterns are supported by the COCO project, the Confidential Container project. Our friends at Edgeless have contrast that can do this, and also hyperscalers like some of the products that I work on also support sort of these feature sets that can be used to protect the servers. So trying to bring all of this together into one concrete slide. So as I described, I see MCPs having a two-layer credential model, right? So the first model is the baseline service accounts. That could be DB URLs, GitHub service tokens, etc., and also agent scope tokens. Both of these have different ways to get the secrets in to the servers. One could be at the boot up time that are really on default or HSM, and agents that have the user context or some an action triggered by the user, or credentials provided by a user that are agents scoped, can be sent to the MCP server after validation with attestation, similar to what the keywords do. So this sort of brings the whole picture together. We have the means of reducing the blast radius and ensuring that we are communicating with a good known MCP server that can reduce the credential leakage and harm that comes with this aggregation, while still keeping LLMs and our agent harnesses useful. Uh, so, so we have the hardware proofs that this is the right image, relaying party verify, and then we have the credential flows going in, and there are several failure modes that can break this chain. If it's a modified container image, it can be caught. If debug mode is enabled on any of the servers, which can make it easy to get these credentials, that can be caught. If it's been a while since the attestation happened, it can be caught, and the same with the host root that's prevented with this model and approach. So we have to be honest, right? Confidential computing is a different in depth mechanism. So TEs are necessary, but not sufficient. We have to pair them with prompt injection prompt injection guarantees that we need to sort of work through. Sampling is another attack that I feel is something that isn't too well known. Like, so it sort of reverses, like usually the in the normal workflow, the agent or LLM talk to the MCP server, but sampling reverses that model, where an MCP server can ask an LLM to generate text on its behalf. So reversing the direction of influence, I sometimes call it an MCP server social engineering the LLM. There's tool poisoning attacks. So all these cannot be prevented by just LLM by TEs alone. So all this have to be thought through. But we do close the privileged host access and the supply chain attacks that are part of the threat model here. So this is what we need for some of the full defense. And like, as I mentioned, we need to think beyond just protecting these credentials to secure MCP servers. We need to have a good permission design, runtime controls, and isolation, as we talked about, to help prevent any of these attacks, credential attacks that happen. So I think we need to think through all these, and then TEs can definitely reduce the attack surface and the credential leaking. And like, what to do Monday? Like, I know folks try to like to end with this. So map your MCP credential surface. Try to figure out what secrets your MCP server has access to. Audit all your host access to AI and your workloads. And ship the MCP capability model, including the isolation that confidential computing provides. So I think that's the end of the talk. I do have a reference implementation, which is based on Azure that I can share further here. And yeah, we can connect with me for any questions.